this is equivalent to the existence of a smooth Hermitian metric on that line bundle with positive curvature. Or equivalently, you may think of a Hermitian metric on OP of 1 or OP of -1 as a Finsler metric on the dual bundle E star, because actually OPE of -1 consists of lines in E star. And of course, having a Hermitian metric on each of those lines means that you have a Finsler metric on E star, namely some sort of gauge function, but without the Hermitian property. And then when you have such a Hermitian metric on a vector bundle, you can define a curvature tensor which has 4 indices, so a theta EH obtained as I times the square of the Chern connection. It's a sum over all indices jk between 1 and n with complex dimension, and the vector bundle indices lambda mu between 1 and the rank of CGK lambda mu DZJ wedge DZK bar tensor E lambda star tensor E mu, where here you compute everything in terms of an orthonormal frame of E. And then you can associate to this tensor a quadratic form on the tensor product of the tangent bundle and the vector bundle E. So it has exactly the same coefficients. Now you pick a tangent vector C, a vector V in the vector bundle E, and then you obtain this sum of Cjk lambda mu, Cjx, Ck bar, V lambda V mu bar, which is just a quadratic form here. In a very standard way, E is said to be Griffiths positive. This was introduced by Griffiths in 1969. If at any point Z in X, then this quadratic form takes strictly positive values for all non-zero vectors C and V. A stronger positivity concept is the concept of Nakano positivity, introduced earlier by Nakano in 1955. Namely that at every point Z in X, then if you take any tensor tau in Tx tensor E, and not just decomposable tensors of the form C tensor V, so now you take any tau J lambda, then the same quadratic form should be strictly positive. So you have more tensors, so it's a more restrictive condition. And of course, by definition, the Nakano positivity implies Griffiths positivity. And it's also well known that Griffiths positivity implies the positivity of the associated line bundle OP of 1, and therefore E is ample in the sense of a Hartree. Okay, and yeah, so this is just what I explained. Now you have another concept of positivity, which is dual Nakano positivity. In fact, in that case, you replace E by E star, and if you compute the curvature tensor of E star with respect to dual metric H star, then you get minus the transpose. So what happens is that the indices lambda mu are twisted, because you replace the frame E lambda by E lambda star, dual frame. And if you take the corresponding Nakano positivity condition, it's different because precisely the indices lambda and mu have been twisted. And now, if you require this to be strictly positive, you get another positivity concept, which I call here dual Nakano positivity. In fact, dual Nakano positivity is still stronger than Griffiths positivity because this is insensitive to twisting indices when you take a split or decomposable tensors. But it is better behaved than Nakano positivity because, for instance, it goes easily to quotient bundles. So if E is dual Nakano positive, then any quotient bundle by a subbundle is also dual mechanopositive. This is a very easy calculation from formula given by Griffiths, for instance. And a very speculative conjecture would be that possibly the ampleness of E could imply the dual mechanopositivity of E. So this would be a very, very strong conjecture, but I have no counterexamples. In fact, the more standard Griffiths conjecture is that E ample should be equivalent to E Griffiths positive, but if the stronger conjecture holds true, it will also be equivalent to E dual mechanopositive. One should remark, however, that the ampleness of E does not imply the mechanopositivity of E. And also the Griffiths positivity of E does not imply the mechanopositivity of E. This is easily contradicted by standard vanishing theorems. For instance, if you take the tangent bundle of Pn, it's very well known it's ample. And also you can check that the standard metric makes it Griffiths positive for the Fubini-Studi metric, but it's not Nakano-positive. In fact, if you apply the Nakano vanishing theorem, you would compute Hn minus 1 and minus 1 of P and C. So it's the same Hn minus 1 into omega n minus 1. And then just by contraction, it's the same as the canonical bundle of Pn tensor the tangent bundle. But by the Nakano vanishing, it would be 0 if Tpn would be positive. And this is a contradiction because, of course, this group is non-zero. And there are other very subtle relations between ampleness, Griffiths, and Nakano positivity. For instance, Bernstein has proved that the ampleness of E implies the Nakano positivity of all symmetric powers Sm of E tensor det E for all multiples M. But of course, adding the determinant is a big deal. It increases a lot the positivity. So it's a completely different setting. Okay, so now I'm going to introduce a new concept, which will be of some importance in this talk, which is the concept of total determinant of the curvature tensor. In fact, if you look at the full tensor, you have 4 indices, but you can see this as a quadratic form on Tx tensor E star. This is because you take dual mechanopositivity, okay? So you have the indices are twisted. But now you can consider this tensor product as a single vector space, and then you compute the determinant with respect to that vector space. Okay, so if you want, you may replace J lambda and K mu by single indices, and you take the determinant with respect to all this. And then you raise the corresponding determinant to power 1 over r. It turns out that if you multiply by the standard volume element in the corresponding coordinates, so I dz1, dz1 bar, dz bar, then you get something that is completely intrinsic and doesn't depend at all on coordinates, but depends only on the Hermitian structure of E and the corresponding curvature tensor. So this form is very meaningful for a vector bundle. It's completely intrinsic. It doesn't depend either on the choice of the orthonormal frame. Just if you change, of course, by an orthonormal frame, you get the same determinant. And now a basic idea is that in a very similar way to what people are doing with the standard Monge-Ampère equations for the Calabi conjecture, then you could consider an analog vector equation by assigning this big determinant to be a given positive NN form. And the idea is that if you do this, this might enforce the dual mechanopositivity if you combine this with a deformation argument by deforming something. And if you keep something, if you keep a Hermitian matrix to have a positive determinant, then you cannot have the eigenvalues that go through 0, of course, because then the determinant would vanish. So if you keep the determinant strictly positive, you are sure to remain in the connected component of positive definite matrices. And we are going to consider such a technique in combination with a deformation technique. Okay, so let me explain this continuity method, going back to the case of rank 1 bundles. So in that case, of course, everything is much simpler. The curvature tensor is just a 1-1 form given by minus I del del bar of log h, where h is the metric. And if you fix a base metric h0, then this is the base form omega 0 plus I del del bar of the potential phi, where h is related to h0 by h equal h0 times exponential minus phi. Okay, so this is very standard. And now the equation I discussed just reduces to a standard Monge-Ampère equation, which is from the Calabi-Yau theorem. So omega 0 plus I del del bar phi to the n equals f. And if f is given, Yau's theorem guarantees the existence of a unique solution for this equation, provided that f has the appropriate volume. Of course, the total integral of this by Stokes' theorem has to be the top intersection number of C1 of E. So there's a normalization factor 2 pi, which I may have forgotten. Okay, there should be a 2 pi. I forget it usually. So provided you have this correct volume, then of course, by Yau, you can solve this. And now assume that you deform f as a family ft depending on time, with a time parameter t between 0 and 1. Then by existence of uniqueness, you get a family of solutions giving rise to a Hermitian matrix ht on the line bundle. And if you keep those ft to be strictly positive, then this will keep also the solution to be a positive 1-1 form. So you do not escape from the connected component. Okay, and now I return to the vector bundle equation, okay? But then there is a problem that you have one equation, but you have many, many unknowns, because the Hermitian matrix is actually a matrix of real rank R square. So you have R square unknowns, but only one equation. So this is not enough to have a unique solution. In analysis, you say this is an underdetermined PDE. Of course, the solution might still exist, but you have complete lack of uniqueness and you lose any control on the solutions. So in conclusion, if you want to recover a well-determined system of equations, you need to add precisely R square minus 1 equations. So hopefully in the form of a matrix equation. So you need new equations. And now an observation that comes from the Donaldson-Uhlenbeck-Yau theorem for the equivalence of stability of vector bundles is that if you have a Hermitian metric on the determinant of E, of course, E being ample implies that determinant of E is ample. And then, of course, you get the polarization, omega 0, a positive Kähler form of integral class. And if E turns out to be polystable with respect to this polarization, then by Donaldson and Uhlenbeck-Yau, there exists a unique Hermitian metric H on E, which satisfies the Hermite-Einstein equation. And then the slope has to be exactly 1 over R because of the choice of omega 0. So the equation is just this, that the trace the trace of the curvature tensor theta EH with respect to the Kähler metric omega 0 is a constant times the identity of E. Okay. And if you look at the trace-free part, so you can, when you have an endomorphism U, endomorphism from E to E, you can consider the decomposition into the trace-free part and a diagonal matrix, which is proportional to identity, given precisely by the trace. Of course, it's very easy decomposition of an endomorphism. And then the trace part is somehow an identity because of the choice of omega 0. And therefore, the equation is equivalent to the trace-free equation. But then the trace-free part means that you look at the trace-free part of this, which precisely has rank R squared minus 1. So this is exactly what you need. Okay, to get a perfectly determined equation, you had to introduce this number of new equations, and this is exactly what the Uhlenbeck-Yau-Donaldson equations provide. And if you look at the special case of curves, so dimension of x is 1, then that condition, trace-free condition, means that E is projectively flat. And this is precisely the case that is known by Umemura. So in that case, the Griffiths conjecture is true. That was proved by the dimension 1 case of the Uhlenbeck-Yau theorem, namely the Narasimhan-Seshadri theorem, by using the Hardin-Narasimhan filtration of E. So in fact, by using the Hardin-Narasimhan filtration, you reduce the proof to the case when E is stable, but then it's projectively flat. And then if it's projectively flat with ample determinant, of course, then E is positive. It's a very easy proof for, well, using modern technology for dimension 1. Okay, but then the main problem is that the Hermite-Einstein equation only has solutions when the bundle is polystable. So if it's not polystable, then suddenly you cannot expect to have a solution of the Hermite-Einstein equation. However, if you go back to the proof given by Uhlenbeck and Yau, you see that in a preliminary step, they've proved that there is always a solution, depending on some parameter epsilon, to a certain perturbed or cushioned Hermite-Einstein equation. To be more precise, consider the space of Hermitian forms on E. So here, this is not endomorphism, the quadratic forms. Of course, you can identify to endomorphisms once you have fixed a base Hermitian metric H0 by the standard, of course, way. And if you have an inner product with respect to H0, given an endomorphism Q twiddle, you associate a Hermitian quadratic form Q by this formula, just standard Hermitian geometry. And the trace-free quadratic forms correspond precisely to the trace-free endomorphisms. And in the sequel, we are going to fix a base Hermitian metric capital H0 on E in such a way that its determinant provide by Kodaira the positive Kähler metric omega 0. It's of course always possible by Kodaira. Then you get a metric on determinant of E, and then you fix H0 so that the determinant of H0 is this metric. And then here is the perturb equation. So you have a perturbation term, which is minus epsilon log q twiddle epsilon. So if you don't consider this additional term, then it's just the Hermite-Einstein equation, which cannot have a solution, as I have explained, unless E is polystable. But it turns out that by adding this extra term here, the solution is always exists and is always unique. It's some sort of approximation that is used in the proof of Uhlenbeck and Yau. It turns out that when epsilon goes to 0, these metrics that you get as a solution explode and precisely converge to the Harder-Narasimhan filtration. So it's some sort of metric way of producing the Harder-Narasimhan filtration. But the advantage is that for every epsilon positive, now you have a solution. The reason from the viewpoint of analysis is that this behaves like a friction term. So when you have a pendulum, of course, a theoretical pendulum could oscillate for infinite time. But of course, in reality, you have friction and then it stops. But that friction somehow regularizes the solution and makes it more stable. And here it's exactly the same. So you have a friction term, which helps in producing a solution, although in the limit, as epsilon goes to 0, the limit will explode. It's very similar to what happens for Monge-Ampère equations. If you add here an exponential of epsilon phi, which corresponds actually to the case of negative Ricci curvature. In that case, it's known that the solution always exists and is unique as well. And so somehow this is the vector bundle analog of the Monge-Ampère equation that is related to the case of negative Ricci curvature. Of course, the trace part is somehow given by the choice of our metrics. So you can concentrate on the trace-free part. And then if you concentrate on the trace-free part, then the identity disappears. And then you get an equation that gives you the trace with respect to omega 0 of the trace as an endomorphism without the, well, the trace-free part as an endomorphism, which is just this added perturbation term. Okay, so now I'm arriving to the general setup of what I'm proposing to solve to attack the Griffiths conjecture. So you start with some parameter alpha, which I will take large enough, and you will see soon why. And then you search for a time-dependent family of metrics, HT, depending on point Z in X, on the fibers EZ of E, that will satisfy a generalized Monge-Ampère equation. So you take this huge determinant of the transposed curvature tensor, but then at time t equals 0 at least, you add this large alpha. Because you don't, at time t equals 0, of course, you have not yet solved the conjecture, so you don't know what is this curvature tensor. It might be non-positive, might have some negative coefficients. But if you take alpha very large, of course, whatever is this at time t equals 0, this term will be very large and will make the sum strictly positive. So then the determinant will be strictly positive. And now you want to solve this with a strictly positive right-hand side, ft, depending on time. And now you're going to decrease this by putting 1 over 1 minus t, and at time t equal 1, this will become 0. So if you can solve this for all times, at time t equal 1, this term will have disappeared. And then you get, by continuity, a curvature tensor that will remain in the connected component of positive definite matrices. So it will be dual mechanopositive. But this equation by itself is not enough. So now you had the trace-free rank R² - 1 Hermite-Einstein conditions, which I write here in a simpler form. So I've chosen before some choice of GT, but you could a priori put any right-hand side GT. Okay, so the combination of these two equations now has the correct rank, R². And now the point is you have to choose appropriately the right-hand side, FT and GT, to have any chance of getting solutions. Okay, so now I'm going to enter more into this, this thing. The basic fact is that this is an exactly determined and not over-determined system. So you have exactly as many equations as the number of unknowns, which is the real rank of the bundle of Hermitian matrices, R². So you can start with the Uhlenbeck and Yau solution at time t equals 0 for the cushioned trace-free Hermite-Einstein equation. So then you just take determinant of small h0 to be the base metric that you've chosen, determinant of capital H0. And then you take alpha so large that this thing will be strictly positive in the sense of Nakano. You want to start at a point where you know Nakano dual positivity. Okay. And then if the conditions are met for all times, then as I already hinted, this term will remain strictly positive in the sense of Nakano by continuity. And at time t equal 1, this becomes 0, and you get a Hermitian metric, which would be dual Nakano positive. So this is exactly what you want. Of course, one still has the freedom of adjusting all right-hand sides, and there are many possibilities. So here is a very general form. Of course, the right-hand side could be chosen to depend also on the metric or not. Of course, because this is of order 2 in terms of the number of derivatives, would not be very wise to take higher order derivatives, of course, for the right-hand side. So at most second derivatives, and in fact, for this huge determinant equation, I even propose to take only at most one derivative. And then it's a well-determined system of PDEs. But you want to know if it's elliptic, because when you have an elliptic equation, of course, solving elliptic equations is much better behaved. And in fact, you can easily compute that it's always elliptic, at least if you don't have too much dependence on the second derivative. So the dependence on the second derivative should have a differential that is small enough with this very explicit constant. Of course, if you don't have any dependence on d square here, it's good. So if you don't take any dependence on d square, then actually you get something elliptic, because the principal symbol depends on the curvature tensor, which has second derivatives. So this is second order elliptic. So of course, if you modify the symbol by order 1, that doesn't affect the principal symbol, it will remain elliptic. So actually, this is what I'm going to do. I'm going to take something here that doesn't depend on the second derivative. Okay, so proof. So I'm giving very briefly the formulas. So this is the standard way of computing the curvature tensor in matrix form. So you take H to be the Hermitian matrix and some coordinates. you compute del of h, multiply by h minus 1, and then take I del bar of this. Or you can do this in terms of the associated endomorphism. Then if you take the associated endomorphism, then you should rather consider the Chen connection with respect to the base Hermitian metric, but that's a minor technical detail. Okay, and then let me recall that if you have an elliptic operator P from a vector bundle V into a vector bundle W, and you have an operator P of F given by a sum of coefficients A alpha of X times D alpha F of X, then the principal symbol, if the sum here, it's a mistake, it should be the sum just over absolute value of alpha equal M. So you take only the top terms of A alpha of X C to the alpha, then you get a homomorphism of V to W, and you want this homomorphism to be invertible for all values of C non-zero. So this is the definition of an elliptic differential operator. For instance, if you are on the torus and you take a Laplace operator, then it has constant symbol minus C square, and of course it's elliptic. However, as an operator, the invertibility of the symbol does not guarantee the invertibility of the operator itself. So you may have eigenvalues, and if lambda is precisely one of the eigenvalues, then this operator as an operator between Hilbert spaces, for instance, need not be invertible. But of course, it will always have a finite dimensional eigenspace, so it's almost invertible in the sense of functional analysis. So the almost invertibility is guaranteed by the ellipticity, but the exact invertibility depends on the lower order terms. So now here is my more specific choice for the right-hand side. So here I'm mimicking the rank 1 case for the usual Monge-Ampère equations. So I propose to take a right-hand side which blows up when the determinant vanishes. So it will add some stability, because then it somehow prevents the determinant of HT to approach 0. Because if the determinant of HT would approach 0, then the right-hand side would blow up, and this would not be compatible with the left-hand side. And so somehow this is a more stable equation. So that's like in physics, when you have a basin of energy and you're at the bottom of the basin of energy, then you are more stable. And this is exactly what I'm doing. I'm somehow creating a well of potential where I have more stability for the equation. So this is for the determinantal part. And for the trace-free part, I'm doing the same here with possibly some exponent mu. And again, this logarithm of the endomorphism. And then because it doesn't depend on the higher derivatives of HT, this is always elliptic. And one can check by differentiation that this will be actually an invertible elliptic operator if you choose appropriately the constants, namely for epsilon large enough, not too small. Of course, we know that in the Uhlenbeck and Yau, everything explodes when epsilon goes to 0. So you should not take epsilon to 0 here. So it should be bounded below by some constant epsilon 0. And then you still have the choice of lambda and mu. Well, mu is more or less arbitrary, could be 0. But then lambda, if you compute the invertibility, so it's just linear algebra, in fact, well, it's a complicated formula for the derivative of a determinant. It's a bit tedious. I'm going to give you very briefly a calculation, but not with much details, then you can check that you get an invertible elliptic operator, provided that lambda is large enough, and even larger if mu is not taken to be non-zero. And corollary, under the above conditions, if you start from the Uhlenbeck Yau solution at time t equals 0, then this PDE system will still have a solution for small time. Unfortunately, at this point, only for small t0. You would like to go to time t0 equal 1. I cannot have uniform control for all times. What I can check is the existence for small time. So it's just by the implicit function theorem and standard elliptic theory, but would be crucial, of course, for the application to a more uniform control, and this is the difficulty. In that case, you have to analyze not just the principal symbol, but the total symbol. So you have to look at the second derivative that appear here in the curvature tensor, but also the low order terms, for instance, zero order terms from the determinant. This is just linear algebra. Okay, so now I'm coming to a related concept of volume for vector bundles. So of course, for a line bundle, the concept of volume is very important. If you have an ample line bundle, the top power of C1 of the line bundle is a very important constant. It appears in the Riemann-Roch theorem and so on. And of course, it's also related to the solution of the Monge-Ampère equation. It's related to many facts of intersection theory. And in a similar way, you can introduce some sort of intersection number for vector bundles, which I call the generalized Monge-Ampère volume of the vector bundle. So we have this top NN form, which is given by a determinant of the curvature tensor. In that case, you really have to put 2 pi to get appropriate value. And then you integrate that positive NN form on X. Of course, to get something positive, you have to assume that E is dual mechanopositive. So if you can solve the big conjecture I mentioned at the start, of course, it will suffice to assume that E is ample. But here, because I don't know, I assume that E is dual mechanopositive. Okay, then you can compute this integral and then eventually take the supremum of these integrals for all Hermitian metrics H on E. In case you have a line bundle, it turns out that this integral is independent of H. So you could take the sup, but it's the same for all H because of Stokes' theorem. This is not true for a vector bundle. You have a more complicated form here. It does depend on H. It's not a priori clear whether a supremum is finite, by the way. But I'm coming to this. So in fact, the supremum is finite. And in fact, you can show that this supremum is less than the rank to the minus n times the first rank class of E raised to power n, which is the same as C1 of the determinant of E. Okay, so the determinant of E is ample, so C1 of that E is positive form. You get a positive number, and this integral cannot exceed this. It is not very hard to prove. In fact, it's just a consequence of the inequality between geometric and arithmetic means, because you look at the eigenvalues of this, And the determinant is just the product of eigenvalues. But then if you take the product of eigenvalues raised to the 1 over number of terms, which is nr, it's the rank of Tx tensor E star, then this is less than the arithmetic means, which is 1 over nr, the sum of lambda j. But the sum of lambda j is a double trace. And taking the double trace means that you take precisely the C1 of det E. And so you get, in that case, that this term gives you exactly this right-hand side. And to get equality, you have to have equality between geometric and arithmetic means, which means that all eigenvalues are equal. But all eigenvalues equal mean that E is projectively flat, which is a very rare circumstance. So actually, it can happen that the maximum here is reached, but only when E is projectively flat. So somehow this inequality detects, in terms of intersection numbers, detect projectively flat vector bundles. But on the other hand, if you know that E is not projectively flat, there is no way the inequality can be inequality, and then this number becomes interesting because it's a distant value from this. It's another positive intersection number that probably has a geometric significance. So let me make some concluding remarks. So this is just I explained. In fact, this is an observation of a postdoc at Institut Fourier right now, named Sergei Finsky from Russia. And it's a very simple observation that the equality holds if and only if E is projectively flat. Sergei has many more interesting results in this perspective, including some asymptotic estimates of what happens when you replace E by symmetric powers of E. And it turns out that if you replace E by symmetric powers of E, whenever E is ample, then the symmetric powers eventually becomes dual mechanopositive. So this makes sense, even for E just ample. And then these intersection numbers have an asymptotic limit that can be computed. So it's very, very interesting. I hope that CIA will soon post his work on the internet. I certainly encourage the audience to look at the forthcoming paper by CIA. There is a very easy case, which is the split case. So if E just splits as a sum of line bundles, and the Hermitian metric H on E splits also as a direct sum of Hermitian metrics on the line bundles EJ, then the previous form can be computed, and you get exactly the product of the top intersection numbers of the summons here, the line bundles EJ. So you take the product of top intersection numbers raised to power 1 over R. And the previous inequality of the previous slide, so this inequality here of the Monge-Ampère volume. So the Monge-Ampère volume is just this product of C1 of EJ to the n raised to 1 over R. And then this inequality again is just a form of the inequality between geometric means and arithmetic means. And in that case, you can see that you have equality again, if and only if you are projectively flat, which means precisely that the chunk classes of the summons here are equal. And now it would be interesting to compute the Monge-Ampère volume in case you are not projectively flat. So if the first chunk classes of the summands are different, then you are not projectively flat. And then you know that this is a strict inequality. And my guess is that in that case, this product is exactly equal to the Monge-Ampère volume. It is equal to the Monge-Ampère volume in case you have a split Hermitian matrix, because this is easy to compute. But it's unclear whether you might not possibly reach higher intersection numbers by using non-split metrics. So I don't exactly know. I'm expecting this to be true, but it depends on some sort of delicate distribution of masses, which might be reachable by some sort of redistribution of a metric, maybe some action, some torus action on corresponding to this decomposition, maybe, but I don't know exactly. Another thing is that, well, you want to reach a maximum. So anytime you want to reach a maximum that depends on a function, you have a calculus of variations. So you can compute the Euler-Lagrange equation associated to this. So just remember that the curvature tensor depends on two derivatives. And then if you consider the Euler-Lagrange equation, you have to integrate 2 times by part. And therefore, you see by calculus of variation that the Euler-Lagrange equation has a 4th order operator. So it's a very, very complicated equation that actually turns out to be the vector bundle analog of what is called the CSCK equation. So in case you want to have scalar metrics with constant scalar curvature, it's well known that you reach a 4th order equation. And that's exactly the Euler-Lagrange equation that you get here is exactly the vector bundle analog of the CSCK equation for the existence of constant scalar curvature metrics. So my guess is that well, technology is not yet available for this because already it's extremely hard for rank 1 for CSCK metrics. So I'm supposing that people are going to have a hard time for that case, but who knows? The easier problem here may be solved. My guess is just possibly just toric geometry that could give this. And of course, you have the very nice results of Finsky computing this Monge-Ampère volumes. This is also related to the Fulton Lazarsfeld inequalities for Chern classes. So there are many interesting questions on Chern classes and inequality for Chern forms that could possibly be related to these problems. So now I've reached the end of this lecture, so I will stop, and thank you for your attention.
So thank you very much. Can you hear me? Because I had some issue.
I can hear very well. Yeah.
Okay. So are there any questions?
So I see that Xiaohei seems to be around.
Yes, I am.
So I made some propaganda for your work to come.
Thank you.
So one question, this Monge-Ampère volume can be defined also like for other situation where it's not an ample vector bundle, maybe interesting also to look at in other situation, or somehow it really requires.
What you could do, and it's part of the work of CRA, is to replace E by symmetric powers of E. So if E is ample, then the symmetric powers of E for large powers become dual nagano-positive, so you can compute.
Mhm.
In case the determinant of E is ample, but not E itself, what you can do is to push by twisting E by some multiple of the determinant,
Mhm.
which in terms of curvature could be just a real multiple, because, okay,
Yeah.
so you can take E tensor determinant of E to power P, but then
Mhm.
P could be just a rational number or even a real number.
Mhm.
And then you get a curvature answer. And if this P is large, if the determinant of E is ample, then you will get a positive thing. So it's just a matter of increasing the determinant somehow. So you could
Okay.
you could have some sort of a Hilbert polynomial associated with the determinant of E or with any other ample line bundle.
Mhm. I see. Any other questions? So if there is no other, here there is a question.
So
I
let
think
me
that
say hello to Lucie Devey, who has been a master student here during the first semester. So is Lucie around?
Yeah, I'm here. Thanks.
Hello. Hello,
Hello.
Lucie. How are you?
Fine. Thank you.
Where are you right now? You are in Grenoble, or?
No, I'm in the north of France.
Okay, so maybe it's slightly better. In Grenoble, it's just terrible. Temperature is
Yeah,
like
I can imagine.
37 today. I'm very hot right now. Okay, so there are no further questions.
No, there is a question on chat. So he's asking, can you elaborate a bit on the potential toric approach?
Well, the idea is that, well, let me come back to this huge determinant. Okay, so here, a priori, you take the supremum over all Hermitian structures. Not if E, you assume E to be split. So you assume that E is a direct sum of EJs, which are line bundles, but you might take the supremum for Hermitian metrics that are not split. And then it's unclear whether the supremum is actually the same as the supremum for split Hermitian metrics. But you might try to rotate by using the action of the circle in each factor. Okay, so you can rotate the metric. If you have a non-split metric, you can rotate the metric in each factor and take the average. And if you do this, you reach a metric that is split, because the non-diagonal terms will average to 0. Okay, so the idea is maybe you could show some monotonicity property of this integral with respect to averaging by the toric action. Okay, so you have the RS power of the circle acting on each factor. Okay, so you have this direct sum here. So you multiply the factor E1 by lambda 1, the factor E2 by lambda 2, and factor ER by lambda R. You let lambda 1, lambda 2, lambda R to be complex numbers of modulus 1. You rotate the non-split metric H. Now, if you rotate and take the average, the average will be a split metric because of a very trivial argument. And if you could prove some sort of monotonicity of the integral with respect to averaging, with some sort of convexity or concavity, then it might just prove the result. So if you have such a suitable convexity or concavity, rather, which is not so unlikely, it might be that you have a very cheap proof for the split case. I've not tried, but maybe this is the next thing I should try. Maybe Thierry knows. I don't know.
Yeah, not for the moment.
Yeah.
And I have also a question. So in practice, this flow that you have constructed, you can construct it for any vector bundle such as the determinant is ample, right?
Right.
And do you have some sort of conjectural image of the time existence for this flow? So because you see, your question, it can be restated exactly in the same way that the existence time for the flow is equal exactly to 1. But if you start from just any vector bundle, which just has determinant ample, then you can ask what is it?
Very, very, very good question. I should have explained that. So let me come back to the flow. Okay. In the case of the Uhlenbeck-Yau theorem, you have a solution for every epsilon. When you try to let epsilon go to 0, what happens is that the family of solutions explode. But if you rescale, you have different speed of explosion in different directions. And if you rescale, you exactly reach the Hadron-Arrhenius filtration. So my guess is that the same might occur here. So if you have something that is ample determinant, but E is not ample, you might have existence for small time, and then you reach some T0 for which you will have a Hadron-Arrhenius filtration in which one of the factors might have non-ample, might be non-ample. Okay, so when you reach some critical time when in the Hadron-Arrhenius filtration one of the factors is not ample, then you're sure that you cannot go further. So my guess is that you might understand actually what is the maximum time T0, possibly in terms of destabilization and in terms of the Hadron-Arrhenius filtration and the terms that are needed to be added to get something ample in those parts of the Hadron-Arrhenius filtration. So and of course, to solve the general case probably requires to understand this. So it's a very crucial question, actually, what you raised.
Okay, thank you.
Okay, so I think that if there are no further questions, we can thanks Jean-Pierre for the nice talk. And yes, and end the meeting. Yeah.
Okay, thank you very much, Cristiano, for hosting the conference and providing technical details that were crucially needed for me. Thank you again. So bye-bye to
Thanks.
the audience.
Bye.
Goodbye.
Bye-bye.